Okay. Good afternoon, everyone. My name is Rekha Rao from Sandia National Labs, and today it's my great honor to introduce our semi-plenary speaker, Professor Lucy Zhang. Professor Zhang is now at RPI in the Mechanical, Aero, and Nuclear Engineering Department. She started her career, though, as a professor at Tulane, and then was derailed after Hurricane Katrina and moved to RPI, where she was then promoted all the way to professor. She has interests in computational mechanics and developing robust software products. She spent several years as an NSF program director in a few different areas, including bio and materials and structures. She is an ASME fellow, and she also has a podcast called This Academic Life that you can get on any platform. Lucy is also our USACM Treasurer Secretary, so in a few years she'll be our president. With that, I'd like to introduce Professor Zhang.
Thank you. Thank you so much for having me here. It's such a great honor to be doing this semi-plenary talk at this conference. So today I'll be talking about advancing multiphysics modeling, looking at novel computational methods for complex systems in engineering applications. And just to kind of get started, many of you, I'm sure, know about the 1940 Tacoma Bridge collapse, and this is a full-blown fluid structure interaction failure. And if you know how this all falling apart, you will see it's instability problem, vibration problems, structural failure problems. So, this is a typical example of our everyday life, what we could encounter in fluid structure interactions. And that's me. In 2005, Hurricane Katrina, this is my tour around after the city kind of cleaned up a little bit. So the wind and the flood destroyed all the dam structures, and that was an event that took me to a totally different turn. And so all of those are all considered as multiphysics interactions because there are fluids, there are structures, and there could be other things that are all interacting together. So just to kind of talk about why multiphysics matter. Now, why does it matter? We see it in our everyday life. In biomechanics field, you will see that, say in this particular example, it's lung interacting, right? So airflow going into an elastic lung, it'll expand, it'll contract. And in energy, you can see that there are wind turbines rotating, and then there will be pressure changes, and then there will be flow changes around it. Aerospace engineering applications of flapping wings, and we try to fly as much as efficient as possible like birds, right? So we try to do mimicking a lot of natures as well. So multiphysics really come and it matters a lot in our everyday life. And just kind of because we're in a computational mechanics conference, just a little bit of history on numerical framework that's been out there to simulate multiphysics interactions. Just kind of give you a timeline of how everything kind of evolved over the years. Back in the very early, back in the 60s to 90s, that's the original traditional methods development, a lot of numerical methods where we're looking at finite element methods and finite difference, finite volume. It really depends on what physics you're trying to simulate, and there are appropriate computational methods that are made to suit that particular problem. So a lot of that is really just one phase, let's solve one problem. And then starting in the 80s and 90s, things got matured a little bit, and people start to look at staggered schemes where multiple things can occur and interact together. And 1990 to about 2010, there are various techniques that are coming out to look at monolithic methods and partition methods to look at how to couple problems. And from 2000 to 2020, that's kind of more recent years, people looking at hybrid methods or more advanced methods to model multiphysics problems. And of course, that comes into today. You would not probably see half of the conference that you will see here are all related to machine learning, AI-enabled methods, and all for the goal of getting the methods more efficient and more accurate, right? So that's kind of where things had evolved over the years to solve multiphysics problems. So who are the major contributors? So I'm just kind of listing here because a lot of the cases that we had been dealing with are fluid structure interaction problems. So coming from the 1970s, you probably heard of immersed boundary methods, and that was developed by Professor Paskin at NYU. So he initially wants to be a mathematician, and no, he initially wanted to be a doctor, but he wanted to be able to model the heart, so he became a mathematician instead. So he came up with this immersed boundary methods. And then in the 70s and 80s, and there are many other finite element-based algorithms coming out. So for example, arbitrary Lagrangian Eulerian had become a standard in many software tools out there. And I'm sure I'm missing out some of the key contributors here, but I just wanted to kind of highlight some of the ones that we've been working on. And then from the 80s to 90s, there are particle methods, and then there are many fluid implicit particle methods and material point methods, lattice-Boltzmann methods, and then also reproducing kernel particle methods. So particle methods become very popular and very well developed because they are more flexible. You can look at a lot of large deformation type of solid structural modeling as well as fluid dynamics. And 1990 to about 2000, there are further development. For example, a coupled Eulerian Lagrangian method developed by Alex Steiner, which is now part of ANSYS. And then 99, started looking at fictitious domain methods where you can have multiple domains kind of coexisting. And then during my graduate school year, we were looking at, kind of inspired by the immersed boundary method, and we started looking at immersed finite element method and sort of kind of revival. So that's a period of time where we were talking with Professor Paskin and say, how do we really utilize finite element and combine with the immersed methods? And then we kind of put that together. And since then, there have been many, many different multi-physics coupled methods out there that we have been developing. Now, there are many commercial softwares available already. I'm kind of listing quite a few here. And many of them are quite powerful And of course, you have to know how the coupled scheme all work kind of behind the black box in order to use it right. So a lot of multiphysics kind of problems are you need to pull in different tools within the toolbox in order to get it to work. So those are the things out there, but of course it's not ready, it's not purely ready. That's why we're still here today to talk about what can we do better. So just kind of going back to some fundamentals, making a fluid structure as an example of coupling, of multiphysics coupling. So for example, if I have two phases interacting and coexisting in the same computational domain, so what happens? I'm going to have a fluid domain, and then I also have a separate solid domain. And they each represents their own physics. So for the fluid, I can use Navier-Stokes, and typically this equation is being modeled, or the set of equations is being modeled using Eulerian frame of reference. And then on the solid side, typically we look at elasticity or nonlinear elasticity type of framework where we typically use Lagrangian frame of reference. So now you have two different reference frames kind of coexisting together. So what do you do? What do you do with the nonlinearity? And what do you do with coupling? And then what do you do with computational complexity? So all of these things will then all come together and then coexisting. So you have to think about how to take care of them, right? So by each on their own, they are already complex enough, but when you put them together, certainly things will become a little bit more complicated. So typically when we do computational modeling, the question to ask before you do any of these multiphysics simulations is to ask, how do you do the coupling? Are you using monolithic or partitioned methods? How do you discretize it? Are you using boundary fitted mesh or non-boundary fitted mesh? How do you put the different meshes together? And then how do you really solve it? What variables are you trying to solve, and how one is being transferred to another, right? So these are the questions typically you want to really design before you actually execute or develop the algorithm to execute. So just to kind of go back to the first question, how do you choose monolithic or partitioned, right? So typically monolithic ones are the ones that you put entire system of equations into one, right? So you look at both, say, fluid and structure, you put them, all the equations into one, you solve the coupled system for all unknowns together in one shot, right? So you form this monolithic matrix and you solve it. You solve all the variables. And that's monolithic. Now, of course, that comes at a price, right? And then partitioned is when you take one domain, you solve it, and then you take another domain, you solve it, and then you're going to iterate and then until they converge to some criteria that you define. So what are the advantages and disadvantages? So for monolithic methods, they provide a stable set of results because as soon as your solution converge, you will have a stable results because they converged, because you have a solution. And then accuracy is also very much guaranteed as soon as you're able to solve that coupled system. But on the other hand, the partition methods give you a lot of flexibility because you are able to capture each one of the domains very well. It can provide modularity, it can provide flexibility, and it can also scale really nicely. It really gives you that kind of, freedom to do many different things. So if I were to put them on a scale, it really depends on what kind of problem you're trying to solve. Not that one is better than the other. So it really depends on what is the nature of the problem and what are those variables you're trying to solve and what is the best way to solve it. So you make a judgment based on your problem on which way to go. All right, so once you decide that, and then you're going to say, so now how do I describe this? How do I physically use a mesh or points to describe this problem? So if you have multiple faces interacting with each other, you can really separate into two sort of categories. One is a boundary fitted mesh. So in this case, it's a very traditional fluid and like a vibrating cylinder. So one is interacting with another, and then in this case, everything is meshed into one. This is one mesh describing two faces. And then the other side, you can have non-boundary fitted technique where you can have totally separate mesh representing their own domain, one in the background, one in the foreground, right? So that's a non-boundary fitted technique. You can have two separate meshes. So for this one, if you were to put them on a balance, this is, of course, my own personal experience based on the problems that we've been trying to solve. I'm going to tip the balance towards the boundary fitted mesh a little bit because it's so flexible. It's so modular. If you can really solve many different parts on their own, you can have different meshes, you can resolve any problem that you may want to resolve in their own domain. So I want to tip that a little bit. Now, of course, the boundary fitted mesh is also fine if you really want that really precise, exact interface. It's also fast if you don't have to worry about remeshing. All right, so again, pros and cons, depending on the problem, the nature of the problem. So because our work is mostly related to the non-boundary fitted technique, so here I want to talk about how everything is being pieced together. All right, so let's kind of go from the fundamental. I don't have a lot of equations here. I promise, just maybe 2 slides here. So suppose you have two faces coexisting. Say one is fluid, one is solid. They don't have to be, but suppose they are. And there will be an overlapping domain. So anytime that you see a bar here, that means it's overlapping. So in this case, I have a solid structure immersed in fluids domain, in a fluid domain. And because the solids is already represented by itself, therefore the overlapping domain that you see in the background is the fluid. It's fake. It shouldn't be there. All right, so it should be subtracted. So the way we go about it is really coming from the principle of virtual work, coming from the finite element idea, where you have principle of virtual work, where you have the governing equation, the strong form, and then multiply and to get the weak form. And the first term that you see here is the virtual work done by the real fluid. And then the second term here is the virtual work done by the real solid. You put them together, that represents your entire computational domain. And then from there, I'm going to manipulate the virtual work done by the solid a little bit. All right, so I'm going to take apart the ones that's done by the background fluid, and then I will subtract it from the work done by the solid. So if I were to put the two pieces back together, I'm not changing anything. They still go back to the original term, but here I want to kind of take apart into the artificial fluid domain and also the solid domain. Because by doing this, I can then start taking things apart by adding these two parts, the real fluid and the fake fluid together into the entire background fluid. I can only do this if I am looking at the domain, the volume metric sense, rather than the single point sense. So that's the major difference from the immersed boundary method. And then everything that's going on the right-hand side, I'll just call that fluid structure interaction force. All right, so you can think of it as residual force. Now, this residual force really comes from the idea where there is a solid existing or some forces existing somewhere, right? Now, of course, if the solid does not exist or the second phase does not overlap on top of the first phase, then that's all zero, so you don't have to worry about it. Now, by doing this, now I come into one big set of equation where the left-hand side is my background, and then the right-hand side describes my foreground. So that's how I put them together. But of course, everything in the foreground, just kind of repeating over here, rewriting again, it shouldn't be just like existing there. There's some interactions between the two faces that are overlapping on top of each other. So one here is the traction-free boundary condition right at the interface between the fluid and the solid. And then the other one is the no-slip boundary condition. So what happens there is to say, I'm going to let my background fluid to follow wherever the solid goes. All right, so this is the kind of reverse of what you've seen in immersed boundary method, where the solid is always following the fluids. All right, so now what we were trying to do here is the fluid fake, because it's fake, so I can do whatever it needs to do. It follows the solid. All right, so that's kind of where things are, and that's how the two things are coupled together. So if you were to look at all these constraints at the boundaries and the overlapping domain, and then also look at the foreground and versus the background, you will see all of a sudden the whole system got decoupled. All right, so they're decoupled by doing that interface exchange. So now you can look at the solid you can solve the solid using however method you want or whatever reference frame that you want. And typically, you can just take a Lagrangian code and then just use it. And then same thing for the fluid, you can use an existing Eulerian code to do it. Now, Lagrangian, you can use finite element. Eulerian, you can use finite volume, finite difference. It really does not matter by this point, because all you need to take care of is that interface. That's all you need to think of. So once we get there, so over the years, we kind of refined, fine-tuned the algorithm better and better, so we are able to kind of set up a few verification cases. The first case that you see here on the left was a fluid structure interaction where you have a sphere free falling in a 3D channel. And then the one on the right is actually fluid coupling. That one is looking at a multiphase flow. You have a Rayleigh-Taylor test. Right? So those are some standard verification cases that we've done. And then over the years, we also kind of played around with kind of extreme cases. Some are simple cases that we're trying to set up as verification cases. And then one of them is looking at a fiber, right? So you can think of it as fibrous material or biomechanical fibers in a fluid, looking at how they behave, how they flow. So this is a typical, I think this one with the Reynolds number is pretty small, like 200 or something, like 150 or something. So flow passed by a three-dimensional fiber, and you can see how it deforms, and then how the fluid domain get partitioned by the pressure into sort of as it kind of bend over, the pressure get partitioned into the two domains. And then here's another case where we're looking at a splashing, right? So you can think of it as inkjet printing, agriculture spraying, splashing, coating type of problems where you can have a droplet splashing onto a free surface. You can see how the surface is responding to that. And we have another case, just as comparison, how they behave differently based on the different Reynolds numbers. And then we also looked at blood drops hitting on surfaces. And then this one, we actually did look at forensic studies, looking at how the blood drops are penetrating into different types of materials using our algorithm for forensic studies. And so in this particular case, what you saw was a droplet hitting on an obstacle, and then based on the free surface, based on the surface tension, how everything is impacting onto the surface. And then we also had a case where we had a water column hitting an obstacle. In this case, is like a flexible fiber, a short column and a long column. So this represents cases where you have a dam gates, spillway designs. So a lot of these problems all come looking at how the water column passing through and then hitting the wall, and then how it all bounces back. So there are a lot of cases that we tried. And then here's another case where we have a three-phase all interacting together. So we have the air, and then we have the liquid. We also have the solid. So using the way that we had constructed, you can do all sorts of stuff, overlapping on top of each other without having to worry about level sets, where level sets you have to think about, oh, you have three phases. You have to define, like the boundary values of the level, the sets for the different phases. For us, everything dumped onto one on top of each other. You can represent however many phases you want. And then so in this case, it's wave energy harvesting. You can think of it as like a buoy problem. You have a free-flowing water column hitting a ball, and then hitting an obstacle, hitting onto another wall, and then comes back. All right, so a lot of engineering applications there. And then, so this is a work that we started working on with our Sandia collaborators, where we're looking at pressure tank or ship panel type of examples. So in this case, that one is actually a shell. This is a shell representation rather than the actual solid. So you can see a flow, or whatever you think. It could be air, could be liquid, and could be high. This is a high speed, pushing that panel forward and start deforming it, right? So you can see how it partitions the pressure into the two parts. And this one is actually a very difficult problem to do because of the entire thing is sealed through. All right, so, and then this is another case where we're looking at a biomechanics problem, looking at phonation problem, human phonation problems, where we're looking at vocal folds vibration and glottal jet aerodynamics all interacting with one another. So in this particular problem, just to kind of, in case you're not familiar, so as we are talking, we have a pair of vocal folds. We have a pair of vocal folds that's made of 3 layers of biotissues. They all have different properties. And then as the lung pressure pushes through, the air would then start pushing these vocal folds to open. And then the elasticity of these vocal folds would kind of want to go back on, start closing the vocal folds, and then pressure builds up, and then eventually the cycle restart. Right? So this one cycle is the hertz that we are talking about. So it's the vibration, it's the frequency of our vibration. So for female voice, it's typically about 200 hertz. For a male voice, it's somewhere around 100 to 100 hertz. Right, so the frequency of this vibration really characterizes our phonation. Now, what's the problem? The problem is there are a lot of vocal paralysis that we see. So for people like us, we talk and then we give lectures, right? When you teach in class, we give lectures, and all of that is a vibration of your vocal folds as it generates. So we started working on this problem actually about 10 years ago with a physician in Massachusetts General. So Larry Page, you all know Larry Page, lost his voice. He didn't know what happened. Structurally, everything, all the image came out to be pretty normal, and they didn't really know what happened. So then they came to our collaborator, and then the collaborator came back to us and said, so there has to be something related to how everything is interacting together, right? So maybe the efficiency is not there. So it turned out when we do all these images of Larry Page, his sound efficiency is close to 0. He can try, but there's nothing coming out, right? So it's simply the efficiency of his voice is not there. And so we were looking, we said, okay, let's start with something simple. We'll start with a very idealized model of the vocal tract, and then we have a pair of vocal folds, and then we're just trying to generate a sound. So when you look at a vowel sound, so the opening can be different shapes. So for this particular shape of mouth opening is the sound. So anyway, so we kind of modeled this with the proper lung pressure coming in. We're able to simulate this entire opening and close cycle. So you can see here, this gap, even when it's open, is really, really small. We're talking about in the millimeter size, right, or a fraction of a millimeter size. But we're actually the first group who are able to capture, who can achieve the self-sustained vibration. All right, so that means we're not manipulating how the vocal folds is behaving. We're not manually closing down the gap. It just opens and closes on its own, and we can do this for hundreds of cycles, right? So this is a pure acoustics, fluid dynamics, and structural dynamics problem. Very, very complicated. And then, of course, as I mentioned, our way, the reason we want to do this is in the first place is to be able to capture the efficiency of sound. And then we went back to textbook, fluid dynamics, 101, back in like undergraduate level. And we say, what is the best way where we can actually capture where the energy flow, what energy flow looks like? And so we kind of partitioned, we used Bernoulli's method, right? So Bernoulli is where you draw a control volume, you really examine every single term and see where's the input and where do they all go. So kind of, drew that mechanical energy flow, looking at the balance of it, in order to evaluate the efficiency. So here's what we found out, that for the model that we have, which is a normal, healthy female voice, and for this one is about 34.3%, right? So of course, this is very much idealized. And for a real normal human, a 25% efficiency is pretty good, all right? So when you get down to below that and you start to, hear some trouble breathing, more breath type of sound. So anyway, so that's kind of what we did with this study. We're continuing with different type of voice diseases and such. So this is an example for the case that we've been working on with Sandia National Lab, looking at solid impact for shock physics type of problems, where we have a projectile, we also have targets, and initially this is what we used immersed methods that I mentioned, Eulerian coupling with Lagrangian, and then boom, we were looking at this particular problem, and it, at least from this point of view, everything worked really, really nicely by coupling two entirely separate codes together. And here's another kind of toy problem that we looked at, and this is sort of 5 plexiglass balls, and then they're under high pressure gas, and then you can see how they are bouncing off the walls and then start leaving the frame. So these are very much solid interaction. Of course, the fluid is in there as well. So anyway, so that's kind of some of the toy problems that we had looked at. Now, challenges and opportunities. We have so much work to do. As you all know, if you had ever tried to model a multiphysics type of problem, cost remains to be an issue. Like all of these simulations that I just showed doesn't come out in just minutes, or we're not even close to real time yet. So cost remains to be an issue, and then of course some of the solutions you will see at this conference is machine learning, AI algorithms. They will help, right? And stability, when you look at coupled problems, stability is still an issue. So we're still looking at different strategies on improving the coupled systems so that they can be, at least the users themselves can know what is the stable region and what is not, right? So accuracy, of course, still a problem. Adaptive refinement is one solution. My dad worked on finite elements since 1980, right? When he retired, he said, I made a conclusion. He said, no matter what algorithm you're trying to develop, you just throw more points at it, it'll always be better. So that was his conclusion of his entire career. So, and I think, when I was playing with immersed methods together, trying to put coupled systems together, I also noticed that if you are able to somehow do some adaptive refinement at that interface, everything just solve themselves, right? So that's that. And then validation. We have all these problems, great engineering problems that we need to solve, but we don't really have a lot of benchmarks built out there for multiphysics problems. So I think we still need more experiments. We need more VVUQ type of studies. And usability. I want to say if you ever use a software, like a commercial software, or you use the one that we develop, the simulation workflow is a pain, right? So it's always, you input here, you output here, and then you manipulate or write some MATLAB code, and then input somewhere else, and then output somewhere else. Workflow sometimes is the major bottleneck. And I think there are solutions out there. We've been exploring some tools here and there. It still needs work. Right? So there's still work to be done, I think, in many different aspects. And I think we're still far away from solving real complex systems as a whole. We're still solving for components. When we're looking at a problem, we're still kind of breaking it apart and then solve a small part of it at a time. And I think to actually solve a real system, we're not there yet. I don't think we're there yet. Maybe with the speed, with the accuracy, we will eventually get there. And of course, we're always trying to bridge the gap between computational power and engineering needs. And that's going to be a continuous struggle, and that's why we're still here. That's why our field still exists. All right, so I'm going to leave it up to here because I talked about where we have gone over the past decades and where are we going to go? What is our future direction? In the field of multi-physics coupling realm. I think that's for all of us to answer, and I think we're getting closer and closer to where we want to be, but we're certainly not there yet. So lastly, I'm just going to leave that up there. I want to thank all of my sponsors and collaborators and all my students, and That's my website. That's the code that we used to develop. It's open source, and you can play modularly. I mentioned the modularity. That's a major sort of the key component of what we had built, is that you can take a solid part and just solve it. Take the fluids part, solve it. You can put them together and solve the couple problems, right? So you can play with that, and that's the code. And then podcast, so that's the podcast. You can download anywhere, listen to it anywhere. So I will end there, and I welcome any questions. Thank you.
Hi, Lucy.
Hi.
Thanks for a great presentation and for pointing out many of the great challenges that we face when trying to solve these problems. One question I had, I've noticed a lot of the fluid structure interaction work seems to focus on coupling with Navier-Stokes opposed to like a RAND simulation. Mm-hmm. Do those pose extra problems, or is it just a problem yet to be solved?
Yeah, I think they don't pose any problems. Actually, I didn't talk about the vocal folds problem. We actually do use a turbulent model in there. It really depends on the nature of the application. If you need it, it's there. Yeah. So in terms of coupling, we didn't see any issues. Yeah.
You mentioned that the current state of the art is kind of simulating different components and not full systems. Mm-hmm. Is there something in the formulation that scales with the number of materials or components you're simulating, or is it more fundamental, and if we could get the other things right, that would kind of come for free?
I think it's my personal opinion is that we're still limited to the power. I don't think it's due to the description or physical description or the code or whatever. And a lot of it, just that vocal folds problem. That entire simulation, if I were to do about 100 cycles, it took about two weeks. Right, so that's kind of where I'm limiting to. And that's only 2D. It's not because we can't do 3D. We can, we just can't afford it. I think a lot of that is really due to the efficiency of the algorithm, efficiency of the computing power, and a lot of those issues. And if you're interested, my student, we've been working on quantum computers algorithms on CFD. So I'm hopeful that that eventually will solve the problem. But she's presenting, where are you, Malvina? Oh, there. So she'll be presenting on Thursday and to look at how we can utilize some new computers, perhaps, and eventually put all that together.